All right, so we're starting into chapter 18. Chapter 18 is kind of a bringing together of a couple of concepts that we've talked about in different kinds of ways, but we want to explore finally and fully here solutions and solids. So this chapter breaks down into 8 parts, and we're going to be doing this over today and the next 3 days. And my primary goal today in this next 45 minutes or so is to kind of hit the first 2 ideas and basically take us on kind of a review of some things that we learned in Chem 105 that maybe we've forgotten, or at least need to see again. And then tomorrow we'll talk about concentration and colligative properties. On Thursday, we'll talk about colloids and surfactants, and we'll begin talking about solids, and then we'll finish up solids on Friday. So I want to take us back to chapter 1. In chapter 1, very first thing that we talked about in Chem 105 was kind of the idea of pure substances versus mixtures. And we talked about mixtures as being what happens when we have 2 or more things that are combined physically with each other. And a classic example of this is air. Air is a mixture of nitrogen and oxygen gas primarily, and then there's a mixture of other things in there as well. But it's mostly nitrogen and oxygen. And if you remember from Chem 105, we talked about the idea of homogeneous mixtures, those that appear to be uniform. And we refer to those as solutions. And if you continue to kind of stay with us and have followed along as we've been going from chapter to chapter here, you recognize this picture here and the idea of solution solvation. The idea that because of the intermolecular forces and the attractions between the water molecules and the ions in an ionic compound, the water molecules are going to pull those ions off of the crystal and start to surround them with water molecules themselves. And furthermore, what we'll see is, well, a couple of things can happen. So if I look closely here, I see that this sodium molecule is surrounded by 6 water molecules. This chlorine is surrounded by 6 water molecules. And that's called solvation. We've also referred to these as spheres of hydration. The idea that these water molecules are surrounding these ions, and it's the collection of the increase of intermolecular forces formed by those ion dipole forces that allows the ionic crystal to be overcome in the first place. This was all stuff that we mentioned in Chem 105. We also talked about heterogeneous mixtures, where we have 2 different phases present. For example, things like oil and water, where we can't get them to mix together. They don't mix together, and so they separate into 2 different layers. But there is a category that we did not talk about in Chem 105, and that is this third category here, where we have a heterogeneous mixture, but it appears to be uniform. And the reason it appears to be uniform is because at the microscopic level, there is a fine dispersion of the molecules within the medium. We refer to this as a colloid. Now, what is the difference between a colloid and a solution? Well, the main difference is, where is that dispersion taking place? At the microscopic level or at the molecular level? Are we getting true interaction between the molecules and each other? Or are we just getting a sort of blending and mixing of the substances with each other and they're really not interacting at all? That's the primary difference. So we have to come back to another concept from Chem 105. Why do solutions form in the first place? And the main idea that we talked about then and will continue to talk about now is the matching of intermolecular forces. Polar forces attract other polar forces. Polar forces do not attract nonpolar forces. Nonpolar forces do not attract polar forces. Nonpolar forces do attract each other, but in kind of the same way they attract everything else. It's just London forces and entropy of mixing that is the driving force in those. We talked about the idea of like dissolves like. Polar with polar, nonpolar with nonpolar. And when we get into polar with polar, we stretch that definition of polar to basically mean anything that has a charge, whether a partial charge or a full charge. So ionic compounds technically don't have polarity in the sense of, it's not really a dipole. It's a full ripping away of the electrons, but we consider them polar forces because you've got a positive or a negative that is attracting the opposite charge. When forces don't match well, they don't dissolve well in each other. So, for example, I have water here. Water has strong hydrogen bonding intermolecular forces. They interact really, really well with each other. Benzene has reasonably strong London dispersion forces. So even though it does not have polarity, the ring stacking that exists between the benzene molecules does resemble a decent force, at least for a London dispersion force. Why doesn't benzene interact with water? Well, it isn't because the benzene wouldn't get stronger forces out of the deal. It would. It's because the water would lose such important forces because the benzene molecules would begin to separate the water molecules from each other. So if I'm looking, look at this four-stranded water molecule over here. The benzene molecule has separated itself and separated the water molecule from the rest of the water molecule. So this water molecule here now can only interact with the benzene. At best, the benzene can offer it London forces and maybe some induced dipoles, maybe. But for the most part, it's going to offer nothing to help with the massive amount of attraction it lost by losing its London forces. So net result here, not terribly great for the water molecule. Not bad for the benzene. Benzene's forces are going to increase compared to where it was, but terrible for the water molecule. As a result, water molecule doesn't do anything. Stays exactly where it is. This water molecule goes, oh, not so great over here. I'm going to move back to where I was. And the water and the benzene separate. So with these ideas in mind, Okay. Thought I had that question. I don't. Okay, so let's just answer this question generically then. I don't have the molecules here. What kinds of molecules would we expect to be soluble in octane? Would we expect polar molecules or non-polar molecules to be soluble in octane? So it's not in top hat. I'm just asking you now. What kind of molecule is octane? So I've got a massive hydrocarbon chain here. Okay. Let's think back to Chem 105. There are two criteria that need to be present for something to be polar. First, it has to have polar bonds, which means there has to be an unevenness in the sharing of the electrons in the bonds. The second is that it has to be asymmetrical, meaning that the overall distribution of electrons in the molecule is uneven in some kind of way. Well, the main takeaway message, or at least one of the main takeaway messages that we should have come out of Chem 105 with, is that from an from an electronegativity standpoint, from an electronegativity standpoint, carbon and hydrogen are practically the same. So carbon is 2.5, hydrogen is 2.1. And if you remember from our bonding discussion back then, any difference less than 0.5 was considered nonpolar. So the thing that we have here is that we know that the carbon to carbon bonds are nonpolar. The electronegativity difference tells us that the carbon to hydrogen bonds are also nonpolar. And if we look at this chain, what we see is a whole bunch of symmetry, because basically what those carbons are doing, they're all tetrahedrals. So they're just going up, down, up, down, up, down, up, down, this long tube, basically. there's no polarity to be found here. And that's one of the reasons why we find most organic things are non-polar, which is why they don't interact with water terribly well. And so we would expect non-polar molecules to be the ones that were soluble in octane. So I don't know what the question here was, but that's what we would expect. All right, so continuing on. Just again, as review here. Ionic compounds, we know that inside of the ionic crystal, we got these ionic bonds taking place. We know that the ionic bonds are extremely strong. They're held together with something called lattice energy. Lattice energy is the thing that holds together that ionic crystal, and it's based mainly on charge and size. The smaller the ions and the more charged they are, the better they're held together. And yet, we see in many cases, water is able to pick them off and separate them from the crystal, get them to dissolve. And the reason why they're being able to dissolve is because the collection of these ion dipole forces here, these 6 ion dipole forces that are being made, are stronger collectively than the attraction that sodium had to the chlorides in the crystal. And the collection of 6 ion dipole forces to this chloride are collectively stronger than the chloride ions to the sodium ions. And so we call this process solvation or hydration. And that's how it happens. That's why it happens. It only happens with polar solutions because polar solutions have to be able to make that ion dipole force to have it happen. And if the ion dipole force isn't strong enough, then we find that solubility is harder to come by. And so if we think back to, again, thinking about solubility equilibrium from chapter 15, one of the things that we would run into there is, well, why is silver iodate insoluble? Well, a lot of the reasons why have to do with this idea here. Are the ion dipole forces strong enough to overcome the lattice energy, to overcome the force of attraction between the ions in the crystal? We can also discuss the concept of solubility in terms of how much is present in the solvent. So dilute solutions, again, dilute is a relative term, but it discusses the idea of, well, what if I have a small amount of solute in a larger amount of solvent? So we can look at the pictures here, for example, and say, okay, well, if the cup on the left and the cup on the right are both of the same substance. So let's just imagine here that for a second we've mixed up some fruit punch. Someone made fruit punch according to a recipe they found online and ended up with the result on the left. Somebody made fruit punch according to the label itself and ended up with this fruit punch on the right. If they started with the same starting materials, drink mix powder and water, we could easily see, okay, well, wait a second, the one on the left looks a lot lighter. It's got to be more dilute. It looks like it's got way more water, way less of the powder drink mix. It's got to be lighter. It's got to be more dilute. But like I said, dilution and the phrasing of dilute versus concentrated, those are relative terms. We've used those terms in the laboratory. A dilute acid is 3 molar for sulfuric acid, but 6 molar for hydrochloric. Let's talk about some other terms that can be used, though, for describing solubility or lack thereof. In chapter 16, we captured the idea of solubility from the idea of saturation. So when we were calculating molar solubility of cadmium sulfide or molar solubility of silver iodate, we were talking about saturated solutions of those compounds. By definition, a saturated solution no longer can dissolve anything else. At that point in time of saturation, what we see is basically equilibrium. This is where, if we go back to chapter 15, this is where our KSP concentration, KSP calculations start to come into play. At the saturation point, we start to see this solid in equilibrium with dissolved. And we've already done the calculations for what that looks like and how to quantify that solubility. But we're talking about things just qualitatively here right now. So at saturation, at the saturated limit, we're done. We go no further. There is an interesting phenomenon known as supersaturation. And in a supersaturated solution, what you have is you have a solution where we've actually been able to dissolve more than the saturation limit for a given solid. We've actually gone over the solid value. Now, how is this done? Well, it's usually done kind of by cheating a little bit. We know that as a general rule, things get more soluble as we heat them, right? So what if, let's say for the sake of argument here, I took a solution that was already saturated, warmed it up to 50 degrees, and then saturated it at 50 degrees, and then let it gently cool back down to room temperature. Now, a normal solution would eventually go back to saying, oh, wait a second, I'm cooling down here, I'm over my saturation limit, and the solid would start to just naturally kind of crystallize and form in the bottom of that test tube. But for some molecules, for some solutions, that doesn't happen. For some solutions, even after we've cooled it down, it remains a solution. Now we know we're above the saturation limit because we've done that. We've calculated it out. and yet the solution remains one phase. It appears that everything is dissolved. What we have in that situation is a supersaturated solution. Now, supersaturated solutions are what we call metastable, meaning that they are stable to a degree, but in the event that something comes and disturbs that delicate equilibrium state that they are in, they will naturally crash back out into a saturated solution again. Now, what kinds of things can cause that? Simple disturbances. So if you take a stirring rod, for example, and you scratch the inside of the glass, that can create a surface for the crystals to start to crystallize on. And once they have a surface to crystallize on, then they start to crystallize and reform. You can also do this with something called a seed crystal, where you take a small amount of whatever it is that you're trying to dissolve in it and drop it into the solution. And what's really cool is when you do that for certain ones, we've done this most commonly with sodium thiosulfate. When you drop sodium thiosulfate into the supersaturated solution, what you'll see is that as it is dropping down, it is just leaving a trail of snow as the sodium thiosulfate is attaching to it and falling down behind it. But you don't even need that. Sometimes just like things like a speck of dust falling into it is enough to provide a surface for the seed, for the crystals to form again. As we are aware, solubility is generally something that increases with temperature. This is a general truth, it's not an absolute. You can see that there are a couple of cases. So, for example, this cadmium compound is one that actually decreases in solubility with temperature. We see that magnesium sulfate kind of hits a limit and then starts to decrease in solubility. We see that sodium chloride barely changes in solubility with temperature. To understand this more fully, we got to get into the thermodynamics of it. So this is where we have to start getting into the calculations of enthalpy and entropy. And so we know that most salts are exothermic when they dissolve. There are a few that are endothermic. You've experienced those in lab. So in a lot of cases, it's really the entropy that is the driving force. And so it becomes a matter of, well, when does entropy, um, how big is that driving force going to be ultimately? With gases are a little bit different. Gases, generally speaking, do not have a terribly great solubility in water. And the reason for this mostly is because, well, most gases are either atomic, and as atomic gases, well, they don't have poles because they don't have bonds. Or in the cases of things like nitrogen and oxygen and most of your common gases, they're not polar. Nitrogen is nonpolar. Oxygen is nonpolar. Carbon dioxide is nonpolar. Now, some of them do better than others in terms of solubility, but that generally is just a description of their intermolecular force. So the reason krypton and argon are better than carbon dioxide and oxygen They have better London dispersion forces because they're bigger. For polar molecules like sulfur dioxide, we do see better solubility because it is polar. Ammonia is really good at dissolving in water because it's polar. But for the vast majority of gases, solubility is not very great. And the other trend that we want to notice here is that almost universally, the solubility of a gas is decreasing as the temperature goes up. So it's the exact opposite trend as what we saw with most solids. Now, the reason for that is something called Henry's law. Henry's law gives us a relationship between the concentration of a soluble gas in water and the partial pressure of that gas. Now, what it means, first of all, don't worry about copying this equation down. We're not going to actually do any Henry's law calculations. At best, we're going to use Henry's law kind of on a qualitative basis to talk about gas solubility just in general, kind of broad brushstrokes terms. And I'll show you kind of what I mean in a minute, because the most obvious case is something that most of you experience on a daily basis, and that is the beverage industry. But the idea is relatively simple here. Gas solubility is influenced by two factors. One of them is pressure. The higher the pressure, the better the solubility is. The second factor is temperature. And we saw in the previous slide that the temperature relationship is a negative one. As the temperature increases, solubility goes down. Now, to give you a context for this, I want to give you an image. This one. Like I said, the beverage industry is predicated largely on Henry's law because most of the drinks that are sold are carbonated. And carbonation is built on one key factor. You got to keep the bubbles in if it's going to taste okay. So what do? Doesn't matter if it comes in a can, a bottle, or some other vessel like a glass bottle or plastic or something like that. Regardless of what it's packed in, it's packed under pressure. And the reason that we know that it's packed under pressure is what is the first thing that happens when you open it? First thing that happens, regardless of what it is, you hear the gas coming out. That's how you know that it's pressurized. Now, why is it pressurized? Because if you just pack carbon dioxide at atmospheric pressure inside of your favorite carbonated beverage, it's not going to be carbonated by the time it gets to you. Doesn't matter if it's a soda, an energy drink, your favorite adult beverage, doesn't matter. Carbonation requires pressure. Second thing, carbonation, carbonation usually demands cold. Now, in addition to just usually tasting better, we know that if you open a bottle of Coke or something like that, and We know that if you open up a bottle and you put it on the counter, it's going to be freshest almost immediately. And we also know that there's a difference between a soda that you pulled out of the cooler versus one that was just sitting on the table. They might start off relatively the same, but the one that's been sitting out goes flat faster. That's the temperature effect. Because as soon as you open it up, the pressure comes out. And since the solubility is less, more escapes initially out of the room temperature one than out of the one that was in the cooler. So the way that I want you to think about Henry's law is this way. That's the image that I want you to take with you. And that's where we're going to stop for today. So tomorrow we'll get into concentration units, conversions of concentration, and we'll also start to talk about colligative properties, that is, properties of solutions that can be measured based upon concentration itself. Have a good afternoon.